Capacitors. We're going to do a lesson on capacitors. This is the introduction. We'll spend some time with them. Capacitors. Now at some point I may refer to a worksheet, and there are problems there on it. We will work along with the worksheet, but this is the one. So you might want to have this handy. It's on Canvas. It's available on Canvas. Worksheet 1, capacitance, potential energy, energy density, dielectrics, etc. All right, so capacitors. Parallel plate capacitors, to be more proper. So what we'll do is a capacitor is composed of two plates, two metal conducting plates, which are parallel to each other and separated by some non-conductor. So what we'll take here is air as a non-conductor, but here's a plate. It's one of the plates. All right, here's the other plate. So some distance away, let's say here, I'm going to draw another plate. And I'm trying to draw these two plates parallel to each other. That's not too bad. So it's a 3D view. Now you have two plates, two metal conducting plates, which are parallel to each other, and then they're separated by a certain distance. So what we're going to do is we're going to connect this into a circuit with a battery. So somewhere here, the wire begins, runs out, comes down. Let's put some kind of a switch here. Here's a switch. Let's set up a battery, positive, negative terminal, and then let's complete the circuit. The other plate. Here we go. So we have a battery, we have a switch, and we have we have two metal plates. That's all we really have. What's between them is air, so non-conductor. Now, a circuit like this is an open circuit, and there will be no current except for the very beginning. So I mean, once you flip the switch, there will be a current for a short period of time in the beginning, and then there will be no current. Now here's how it goes. So positive terminal of the battery, that's just a big plus. Negative terminal of the battery, that's just a minus. You can think of a positive terminal as a place where you have a bunch of positive charges, and you can think of a negative terminal as a place where you have a bunch of negative charges. That will help you analyze what's happening here. So let's say we close the circuit. Well, before I do that, what we have in this wire here is, well, we have protons and we have electrons, and it is the electrons that are allowed to flow. So because of metallic bond, so let's just draw these electrons here. Now we have more than what I'm drawing, but there it is. And then we have electrons on the other side as well. So there are electrons, there are free electrons in these wires. Free electrons, free in the sense that they can move. So now I'm going to close the switch. And once we close the switch, there, these electrons, the negative charge here is attracted to the positive terminal of the battery. So it's going to move a little. This electron is going to move a little in this direction, and then that one's going to be pulled also, and then this one's going to be pulled as well. All of these are going to be pulled here by the positive terminal of the battery. This one's going to be pulled, and then this one's going to be pulled. You're going to get a domino effect where all of these charges, negative charges, will be pulled. And then what will happen is, it's not just the electrons within this wire that will be pulled towards the positive terminal of the battery, but you also have some electrons pulled from the plate itself. Now, if the electrons from the plate are pulled into the wire, then the plate itself ends up with a deficiency of electrons, and so with a positive charge. So this plate here is going to be charged to a certain positive value. Let's put let's put 2 pluses on it. Now these 2 pluses will then attract electrons from the other plate to come up to the surface, and then while that's happening, we're going to end up with a negative charge on a surface here. So I'm going to put minus and minus. And then you're going to end up with these other electrons being pulled in this direction as well. This one pulled in this direction, pulled in this direction, this one pulled in this direction. While at the same time, the negative terminal of the battery is helping to push these. So push, push, and pull, push. All of this is going to move. Until eventually the battery runs out of steam, if you will. I mean, the battery has a certain amount of voltage. There's a certain voltage delta V here. And depending on how big this voltage is, that battery will be able to generate more or less of a push on the electrons within the circuit. So at some point, these electrons will no longer be able to go anywhere because the battery will, if you will, run out of its steam. It's limited by its potential difference, by voltage. So for a very brief period of time, right after you close the switch, electrons will flow in a circuit. And then they'll stop. Once they stop, you will end up with some charge, positive Q, on one plate and some charge, negative Q, on the other plate. The two Qs will be the same magnitude-wise. I mean, if you pull one positive on one plate, you're going to pull one negative on the other plate, right? If you pull 10 positives on one plate, you're going to pull 10 negatives on the other plate. So the two Qs must be the same. That's important. And then the second thing is that you're going to end up with an electric field between the two plates. There's a positive plate, there's a negative plate. Electric field is going to show up wherever you have a charge. You do have charges there. So there's going to be an electric field that points from the positive to the negative. There it is. And in fact, often enough, what we do is we're going to approximate this electric field set up here. I'm going to draw it a little differently on the side here. Here's one plate, here's the other plate. This is just a 2D view. All right, so this is a 2D view. This was a 3D view. In a 2D view, you end up with a positive charge here, negative charge here. I'm drawing 3, and maybe I'll put the third one there. And then you have an electric field that points from left to right, and there is a potential difference between, I should have kept the, that's all right. Should have been consistent with colors, but there's a potential difference between the two plates. From one plate to the other plate, there's an electric field here. And we often enough in electronics approximate we treat this electric field here between the two plates as if it was the electric field of two infinitely large plates. I mean, it's not true that this runs to infinity. It's not true that this runs to infinity and so on, but to a reasonable approximation we can use that. And so what we have is that even though that's not quite true, if you recall, when we had like a plate, and this plate, if this plate was said to be infinite and then there was a charge packed on it, then we were able to calculate, we figured it out two different ways, Gauss's law, and then there was another method we used, but you could find an electric field. Electric field is constant everywhere in this space. It just points straight up wherever you go. However far out you go, doesn't matter, electric field value is the same. And that was sigma over epsilon naught. Sigma is the charge density, so sigma was Q over A. Right, that was it. Now if you have two plates, and let's say you have a negative plate, right? So if you have a negative plate, whether this is plus or minus here is irrelevant. The electric field is going to be sigma over epsilon naught anyways. The only difference is going to be if this is positive, then electric field points away from it, from the plate. But if the charges are negative, then electric field points towards the plate. So maybe I'll draw another one here. Here's a plate, negative charges. The electric field is just going to point towards them, right? But however far out you go, the electric field will have the same value, and it's just going to be sigma over epsilon naught. So it's the same equation, but different direction for the electric field. And again, sigma is the charge density, so Q over A. Now, if we put two plates like this together, one next to the other one, then we just combine the two electric fields. In fact, what you're going to get is there's an electric field that points in this direction away from the first one, and there's electric field that points, it'll double up. You're going to end up with a double effect because now you have two of these plates. So on the outside you would have electric field that points like this. But what we're interested in is the electric field between the two plates. And since one plate gives me this, the other plate gives me this, the total electric field on the inside between two infinitely large plates, so this also extends to infinity. So the electric field between two infinitely large plates is just going to amount to, oh, you know what? That's not true. I think this was 2 times epsilon naught, 2 times epsilon naught, and so then what we end up with is sigma over epsilon naught. That makes more sense to me. I'm gonna double check this. All right, so we're good. So we did need 2 in here, and we end up with this as the correct equation. So we have the electric field, we know the equation for the electric field. We also know that we end up with 2 charges, one on this side, one on the other side, and we have then the potential difference. Now we're going to define something. These capacitors are very useful. A capacitor is just, 2 plates like that. Capacitors are very, very useful in electronic circuits. combined with, well, there's always some resistance. So with resistors, and they're even embedded. Certain capacitance is embedded even in transistors, and transistors are building blocks of all computational pieces of electronics. So you do have capacitors and capacitances within your cell phones. They're there in laptops and just about anything that has a microcontroller will have these. So they play a significant role in electronics and electrical engineering. And the only thing I've given you so far is the concept, the structure of the capacitor. It's how we build it. This equation of the electric field between the two plates. Now I'm going to define something new, and that is the capacitance of a capacitor. So, well, let's just go ahead and do it. We're going to say that C is Q divided by delta V. This is the definition of capacitance. Definition of capacitance. And capacitance is an intrinsic property of a capacitor, like a mass is an intrinsic property of matter. Capacitance would be some property of a capacitor, and we define it this way because, well, you'll see in a second why it's convenient to define it this way. In any event, within a capacitor, if it is charged, you end up with a Q that is non-zero and a voltage V, delta V, that is non-zero. So you can use these two to try to come up with something. And turns out if you divide Q by delta V, you end up with some, it gives you something useful. And so we'll define this ratio as C, where C is the capacitance. Units of capacitance are farads. So I should include this here, F farads. All right, and now what we're going to do is we're going to combine this with that, and one more thing. Delta V, let me see if I can do it. Let me see if I can do this. So what I want to do is I want to get rid of that. And I want to write the equation here for delta V. Since the electric field is constant, in this, between these two plates, we can use the following: E times delta D. We can use this expression for delta V. I mean, what it should really be is gradient of V is the electric field. But it turns out that this equation becomes this if the electric field is constant. In this case it is. So we're justified in using this equation here, and we will use it. Delta D is the distance between the two plates. Right, so delta D, that's the distance between the two plates. And this one here, that's delta D. So let's combine these three equations and see what we get out of it. And how do we do it? Well, oh, I see. So here's what we could do. We could modify this one a bit by writing that this is simply Q over epsilon naught times A. Now I have an expression. From here I can pull an expression for Q. So this would be electric field times epsilon naught times A equals Q. I'm going to take this equation for Q. I want to plug it into this Q here. So combining these, again, this equation and this one here, combining them, I'm going to end up with capacitance equals electric field times epsilon naught times A over delta V. But then what I can do is, like, I guess I could do a couple things, but here's one of them. I could take this equation and plug this in for delta V. So what I end up with is C equals E times epsilon naught times A over delta V, where that's just E times delta D. And that's going to cancel out the electric field. And now here's the result that is significant. And we obtain it because we define capacitance by this equation here. So what we have is that capacitance of a capacitor is epsilon naught, which is just a constant, times the area of one of the plates. This is A, this A here, and that's the A that comes from, it's just the area of one of the plates, not both plates, but one plate, over D. I'm just going to put D here, where D is the distance between the two plates. Now, if you look at this equation, A is just the area of the plate, D is the distance between the two plates, and this is a constant here. So capacitance, as defined by Q over delta V, can be expressed in this way. And then note that capacitance then depends on nothing but geometry of the capacitor itself. Now this is very useful for circuit analysis. It doesn't matter what is the voltage across the capacitor, it doesn't matter what is the current through the capacitor, regardless of the two values of the current and the voltage, capacitance stays the same. That's very useful for circuit design. If you can slap a number on a capacitor by designing it to have certain specific geometrical dimensions, then that's great, because then you can, regardless of where you put this capacitor into what circuit, the capacitance of that capacitor will stay the same. All right. So these two equations is what you need to be keep in mind. And then maybe what I'll do is I'll draw like a picture like this, where we have, here's one capacitor, here's one plate, here's the other plate, there's our capacitor. So area A is just the area of one of the plates, and then distance D is the distance between the two plates. That's all you need. And then there's a wire, and there's a wire that goes off. Here's the capacitor. Okay, I gave you the equations, I give you the concept. We should solve a problem. So from this worksheet here, in the first, there are a couple sections there, but in the first section there are 4 problems, I think, that you are to that we want to solve. There's one that I'm going to solve, and I'll give you the rest as a homework. So let me set these up. So in your textbooks, on page 808, numbers 1, 2, and 3. Now I'm going to solve the first one, and then these 2 will be a homework. All right, so page 808 in your textbooks. All right, so here's the first one, and these problems tend to be trivial. So all right, so problem 1, here's how it goes. The plates of a parallel plate capacitor are 2.5 millimeters apart. I'm going to draw a picture for this, and I'm going to put everything that they give me here. So the distance between the two plates, this is going to be the positive plate, this is going to be the negative plate. The distance given is 2.5 millimeters. Is that what I said? Yeah, 2.5 millimeters, so times 10 to the negative third of a meter. And each carries a charge of magnitude of 80 nanocoulombs. So I have a Q here, and I have a Q here. The two Qs are the same, one is plus, one is minus, but each one is 80 nanocoulombs. So that's all I'm given. Now there's a little more. The electric field between the plates has a magnitude of 4 million volts per meter. So there's an electric field between the two, from positive to negative. We say that this field is constant. That's almost true. And so we're going to put here E equals what 4 million volts per meter. Volts per meter are the same unit as newtons per coulombs. And in case you're wondering, because sometimes we use one or sometimes the other, so volts per meter is the same thing as newtons per coulombs, and it's not too difficult to show that that's the case. We won't. I won't do it though. So what is? We have 3 questions: A, B, and C. In part A, what is the potential difference between the two plates? Let me state it like this. Let me just state it like this. Unknown are the voltage between the two plates. What is the potential difference between the two plates? What is the area of each plate? So A is a question mark. And then what is the actual capacitance? So C is also a question mark here. All right. So we need the voltage. We have the equation for the electric field. What we need is the voltage, area, and the capacitance. So I'm going to start with the electric field. The equation for electric field is, well, two ways to state it. One is sigma over epsilon naught, but that's not going to be very useful for us. So instead I'm going to state it as the electric field is, remember sigma is just charge over the area. So this is Q over A times epsilon naught. This equation will be useful because I have E, electric field, and I have Q, so I can easily calculate A. So what I get out of this is 4 times 10 to the 6th equals Q, which is 80 nanocoulombs, so times 10 to the minus 9th. This divided by area times epsilon naught. Now epsilon naught is a constant, 8.85 times 10 to the minus 12. And from here we can get the area A. All right, so let's see what we get for that. All right, so what I got is that the area here is 2.26 times 10 to the minus third, and it would be in meters squared. So I have the area, so that's done. Okay, now I can calculate, actually now I can calculate the capacitance, because now that I have the area, I'm gonna underline this. Maybe I'll box it. There we go. Capacitance, the equation for capacitance, that was epsilon naught times A over D, and I have everything I need. So 8.85 times 10 to the minus 12 times the area, which is 2.26 times 10 to the minus third, divided by distance D, which is 2.5 times 10 to the minus third. Oh, look at that, that's a win. Well, yeah. Well, this goes away. And then this is almost 1. It's very tempting to say that it's 1, so we'll just make it 1. 8.85 times 10 to the minus 12 and farads. Oh, look at that, picofarads. 10 to the minus 12, that's pico, and you will often run into that. So I'm gonna actually put it this way. So this is 8.85 picofarads. Pico stands for 10 to the minus 12, right? So you have milli, micro, nano, and pico now that you need to be familiar with. Milli, this one here, that's 10 to the minus 12. This is 10 to the minus 9th. This is 10 to the minus 6th. And this is 10 to the minus 3rd. Okay, so we have a capacitance, we have the area, and then what else is left? The voltage. We could do it a couple different ways, and you should get the same answer. So for example, you could use this electric field equals delta V over D, and you would get the answer. But you could also use, which one was it? C Q over delta V. You could also use C equals Q over delta V. It should not matter which equation you use. You should get the same answer. So let's use the new equation. Let's use this one. Capacitance, we got that. We're looking for voltage. So then the voltage is going to be Q, which was 80 nanocoulombs. So 80 times 10 to the minus 9th divided by the capacitance, which is 8.85 times 10 to the minus 12. And so then the voltage equals, let's see what we get. $9,000 volts. So we get 9,000 volts. That seems like a big number. I'm gonna put it here. 9,040 volts is what I get. Why would we have so many volts in a capacitor? Well, I checked the answer in the back of the book and apparently this is correct. So, but 9,000 volts across a capacitor, that's a lot of voltage. I mean, if the distance, you'd have electrons shooting through the air. There was air between that. You'd have a breakdown of this one, but anyways, so there's that. Now what's yours to do are problems 2 and 3. That these two here are your homework, and I think this will do. So on Monday when we come back to school, I think we'll just move on and do capacitors with dielectrics, but that's to come. Okay, that's it.